Is a roller coaster launch about the top speed, or is it about the intensity? Not all launches are created equal. From the mechanical rip of a pinch wheel to the invisible pull of a magnet, the way you get to 80 miles per hour changes the entire experience. It's the difference between a steady push and a sudden explosion. Today, we're peeling back the steel skin of these machines to look at the massive infrastructure and the rigid physics required to make them happen. This is the engineering of the launch and the search for the ultimate thrill. Welcome back to Squared Node. We start with a system that feels more like a drag strip than a theme park, the friction launch. If you've ever launched uphill on an iconic B&M coaster, you've felt this brute force engineering firsthand. Instead of magnets or cables, this system uses many high-torque electric motors, each driving a set of heavy-duty rubber pinch wheels. But the real engineering is hidden in the park's power grid. To spin these motors simultaneously, the demand is astronomical. To prevent a local brownout, these systems rely on dedicated infrastructure, often massive flywheels or capacitor banks that store energy slowly over several minutes, only to dump it all in a violent 3-second burst. From a reliability standpoint, this is redundancy 101, because each motor is an independent unit. If a single motor fails, the other motors simply compensate. It's arguably the most reliable high-speed launches in existence, but it's a constant battle against the friction coefficient. If the wheels are wet or the rubber is worn, the system loses its bite, proving that even the most advanced electrical grid is still at the mercy of simple mechanical grip. But what happens when friction isn't enough? That's where we move into the heavyweights, hydraulics and pneumatics. This is the sledgehammer of coaster engineering, but it comes with a strict physical ceiling. The math here is rigid. Launch force is a direct product of cylinder diameter and fluid pressure. In a hydraulic system, we use pumps to push an incompressible liquid, usually oil, to move a catch car. To get that instant explosion of speed, we store energy in nitrogen accumulators that act as a massive gas spring. However, this creates a major engineering constraint. To launch a heavier, larger train, the cylinders, valves, and catch car cables would have to be so massive they'd become physically impossible to house within a standard track. This is why these rocket coasters usually feature lighter, shorter trains. It's a trade-off. You get the most violent acceleration on Earth, but you live in a constant cycle of maintenance, fighting high-pressure leaks and cable tension. It's raw power, but it's a temperamental beast. Before the modern launch era, we had the chain lift. It might seem low-tech, but the classic chain lift is a structural feat hidden in plain sight. It's the definition of structural honesty. An industrial steel chain for a 300-foot giga coaster can weigh tens of thousands of pounds. The ride structure doesn't just support the riders. It has to support the massive dead weight of the chain itself. Hidden deep within the lift hill or beneath the station is the engine room, massive, high-output motors and gearboxes that must maintain perfect tension at all times. Even a slight amount of slack can cause a mechanical echo that stresses the entire lattice structure. This is the slow burn of engineering. The rhythmic clink of the safety dogs engaging the chain is a psychological masterclass. It builds a level of suspense and anxiety that a fast launch simply can't replicate. It's the oldest engine in the industry, and because it's nearly 100% reliable, it's not going anywhere. Finally, we arrive at the modern king, the LSM, or linear synchronous motor. Here, we move away from mechanical tension and into the precision of the air gap. There are no contact points here, only magnets. Magnetic fins on the bottom of the train must pass through electric stators with millimeter precision. If that gap is off by just a few millimeters, the system loses efficiency, or worse, risks a catastrophic strike. The magic is in the logic loop. The system tunes the magnetic field in real time, monitoring the system to know exactly where the train is at every microsecond. But the real engineering win is the rollback. In any other system, a train failing to clear a hill is a logistical nightmare. In an LSM system, the magnets instantly detect the reverse motion, flip their polarity, and act as a contactless brake, often allowing the computer to pulse the train and relaunch it from a dead stop. It's smooth, smart, and incredibly reliable. But does that digital precision feel too clinical? Some enthusiasts say it lacks the soul and vibration of the mechanical era. So where does your loyalty lie? Do you want the decentralized reliability of the pinch wheel, the raw, pressurized violence of hydraulics, the structural honesty of the chain, or the digital logic of the magnet? The quest for the ultimate thrill is a battle between mechanical grit and digital precision. Let's debate the physics in the comments below. See you in the park. This is Squared Node.